Today's lesson is on angles of a polygon. A polygon is a many-sided figure which we name by listing consecutive vertices in order. So we have two examples of polygons here. Here's one, here is the second one, and this polygon right here, we will call that polygon ABCDE. A polygon is made of segments, so there's no curves in it. It can't cross and it has to close. So here are some examples of different objects. So for instance, this square right here, that is a polygon. That's a polygon. It's made of segments, it doesn't cross, it has to close. This triangle right here is also a polygon for the same reasons. Now in this figure right here, this is not a polygon because it crosses. So this is not a polygon. And our last figure right here, this has a curve in it. So it's not made of segments, so therefore it's also not a polygon. There are two different types of polygons. We have a convex polygon and a non-convex polygon. There are a few different ways you can use to determine what type of polygon you have. I think the easiest way is the rubber band test. I think that's the easiest for me visually, so I'm hoping that works for my students as well. And what that means is if you were to put a rubber band around the figure and it touches all vertices, then it's a convex polygon. So for instance, in this polygon, here are all my vertices. If I were to put a rubber band around this, it would in fact touch all my vertices. It would be tight, but it would do so. So that makes that a convex polygon. The other type of polygon is a non-convex polygon, or we sometimes call that a concave. So it's concave or non-convex, and what that means is it does not pass the rubber band test. Now remember, the rubber band test is if I put a rubber band around my polygon and it touches all the vertices, then it's a convex polygon. So I'm looking at this first figure. Here are all my vertices. Now if you can visualize putting a rubber band around this, it would hit only the outside, right? The rubber band wouldn't dip inside there. So that would make this a concave. And also sometimes it's easy to remember that it kind of caves in. There's a dent in. And that means that it does not pass the rubber band test because it did not touch all the vertices. In the second polygon we have here, we have the same idea. Here are all my vertices. If I were to put a rubber band around this figure, it would not hit this one inside. So this would make this a non-convex or a concave. Again, the wording is one and the same because it does not touch all of the vertices when putting a rubber band around the figure. Another way we classify polygons is by the number of sides. A triangle has 3 sides, a quadrilateral has 4 sides. Some of these are probably familiar to you. Pentagon has 5 sides, a hexagon has 6 sides, heptagon has 7 sides, octagon has 8 sides. Those you're probably familiar with. As you get larger, a nonagon is 9 sides, and a decagon has 10 sides. We use this phrase n-gon, meaning it has n sides, just to talk about something generically about a type of polygon without saying specifically the number of sides. Now what you have here in the examples, that's a quadrilateral, has 4 sides, and again here's my triangle, which has 3 sides. A special type of polygon is a regular polygon. And what that means is it's equal angular and equilateral, meaning all angles and all sides are congruent. So for instance, in this one right here, this is a pentagon because of the fact that it has 5 sides. Now we call that a regular pentagon because the angles and the sides are both congruent. In this other figure, this is a hexagon, and again, it's a regular hexagon because of the fact that all the sides and angles are congruent. In the last part of today's lesson, we're going to look at a theorem talking about the interior angles and the exterior angles. So here's a theorem about an interior angle. It says the sum of interior angles of a polygon, use the formula n minus 2 times 180. So let's talk about that. If I had a pentagon, which is 5 sides, so the n is the number of sides, I would take 5 minus 2 and then multiply that by 180. So 5 minus 2 gives me 3 times 180, and then my total number of degrees in the interior of a pentagon is 540 degrees. Now, looking at the bottom, it says right here, it says if each interior angle, if it's regular, we can again do something a little bit different with the formula. If I know the entire pentagon has a measure of 540 degrees, and I know it's a regular pentagon, meaning that all the sides and the angles are congruent, then I can use this formula right here. So I'm going to do the same thing. I have n minus 2, which is going to be 5 minus 2, times 180, which we already found to be 540. We'll divide that by n, which is the number of sides, which is 5. And when I do that calculation, I end up with 108 degrees, which means each interior angle of a regular pentagon has a measure of 108 degrees. Now, how do we get this formula, this n minus 2? Well, if you think about it, every triangle has a measure of 180 degrees. So what we're really asking is how many triangles is in each pentagon. So if I'm looking at a pentagon and I just pick any vertices, how many triangles can I draw? Well, I would certainly skip the ones that are right next to me. And there's one triangle there. There's another triangle there. So what happens is I have 1, 2, 3 triangles. 3 times 180 gives me 540, which is why I have to subtract it by 2. The 2 that I'm subtracting is actually the 2 sides that are closest to the vertice that I'm dealing with. And again, this formula, the n minus 2 times 180, will work for any polygon. Now, if we're looking at the sum of the exterior angles of a polygon, it's always going to be 360 degrees, and that's for all figures. So if I ask you for the exterior angles of a polygon, if I want the sum for a pentagon, it's going to be 360. If I want the sum of the exterior angles of a hexagon, it's going to be 360. The only other thing I can do with that is if a polygon is regular, meaning that each angle and each side is the same, if they're congruent, then I can figure out what each exterior angle is. I would simply take 360 degrees and divide it by the number of sides. So again, for instance, for a hexagon, if it's a regular hexagon, I definitely need to specify that. If it's a regular hexagon and I want to know the angle measurement for each exterior angle, I would simply take 360 divided by 6, which is the number of sides, and I would get 60 degrees. And that would tell me the measure of each exterior angle of a regular hexagon.